and and after that, she did her postdoc at Princeton University, and now at University of Chicago, she's performing advanced research, experimental fundamental physics using a platform of orbital patterns and molecules. So today she's going to talk about simulation with ultrapolar molecules and the concepts.
Thank you so much. Before I get started, I'd like to thank the organizers. It's my first time here in Urbana-Champaign, and I'm very lucky to give the opportunity to talk a little bit about past and future research with a wonderful quantum-loving audience. So the title of my talk is broadly Opportunities for Quantum Simulation with Ultrapolar Molecules, and about at the midpoint of my talk, I will tell you what I mean by ultrapolar. But first, because this is quite a general audience, let me motivate why we like to use atoms and molecules for quantum simulation. First, let me explain the types of problems we're trying to address. There's a host of interesting science questions, broadly from quantum materials science or quantum chemistry, where the physics is governed by strongly interacting systems, let's say electronic matter. And these materials are so strongly interacting that they simply cannot be modeled by classical computers, at least not effectively, and yet they have a whole host of interesting, potentially technologically groundbreaking applications. And let me give you two specific examples. Of course, there are a wider range, but to be specific, a whole host of quantum optimization problems can be mapped onto finding the ground state of a many-body spin Hamiltonian. And also, overarching holy grail for many condensed matter physicists has been in the past half century how to engineer materials to superconduct at room temperature. And one might decide that the so-called cuprate superconductors are very difficult to engineer and understand from first principles. Why not map it onto a much simpler, although still tricky Hamiltonian, famously called the Fermi-Hubbard, which might recover some of the phenomenological features of the cuprate family. And from this way, we can kind of understand quantum materials from the bottom up. So my platform and the platform many people use are systems within AMO, atomic, molecular, optical. So let me break down why I think this is one of many compelling platforms to simulate traditional, well, what I'll call traditional chemistry. Here's a beaker of condensed phase molecules at 300 Kelvin, or condensed matter physics. Here's some electron moving around in a crystal lattice at the angstrom level. Well, number one, we can place cold atoms and molecules in very fancy tailored optical potentials and actually image them. The light matter interaction of these atoms, molecules, and the laser is very well understood from first principles. These are very clean without defects. And crucially, because these are heavy particles compared to electrons, they have slow dynamics on observable timescales, such as microseconds or milliseconds, rather than the typical electron dynamic timescale, which may be attosecond, picosecond. Crucially for us, the atomic or molecule-molecule interaction are tunable in ways that I'll explore later. And that gives us certain features to tune over a broader range of phases of matter. And finally, the large interparticle spacing, these lattices are usually generated from visible or near-infrared light. The typical length scales are about 1 micron, which is far easier to resolve in situ, and especially when it comes to quantum dynamics compared to electron and solid materials. So if you take away nothing else from this talk, try to remember that in many cases, AMO platforms are a nice slowed down, blown up, impurity-free simulator for quantum materials and chemistry. Let me just show you some of the quantum or some of the optical toolbox that modern AMO researchers can bring to bear on some of these problems. I've already mentioned optical lattices. Many of you are experts. For those of you who are not, just think about interfering laser beams together, and you can perhaps form standing waves, right? And if you tailor your potentials just right, you can form crystals of light made out of periodic or quasi-periodic potentials, as you see pictured here. But you can do even better than periodic or quasi-periodic potentials. With the technology of spatial light modulation or deformable micromirror devices, you can actually pattern arbitrary images onto your atoms. I love this cartoon of Bose and Einstein. They form a mask that is created by spatial light modulation and projected on a cold gas of rubidium atoms that formed a Bose-Einstein condensate. And finally, many in this audience work with optical tweezers. They're a highly versatile platform where you can pluck single particles in the waste of a highly focused Gaussian beam, and you can dynamically rearrange atoms and molecules with one-dimensional, two-dimensional, even three-dimensional arrays of optical tweezers. So in particular, all of this optics technology, as well as cold atom technology, has spawned a very rich field of what I'll call simulation of strongly correlated systems, quantum many-body system with cold atoms. I cannot give you a full overview of all the exciting work that has happened in the last 2 decades. There's too much to cover, but certainly people have been probing interesting topological phases of matter with, let's say, Rydberg atoms, beautiful probes of exotic quantum spin liquid phases by the Harvard group, as well as modeling potential exotic superconductivity with Fermi-Hubbard simulators using cold atoms. And so one might question, if this field is so rich, what is the benefit from upsizing our quantum toolbox to include not only atoms, but molecules, which in my physicist brain are just 2 atoms? And the answer is yes, you pay a high price in experimental complexity. These experiments with cold molecules are more difficult than experiment with cold atoms in many ways. However, you're able to enlarge the quantum toolbox. I would claim optimistically, anything in theory that's possible with cold atoms is also possible with cold molecules, but the inverse is not true. Molecules have richer internal degrees of freedom, such as the ability to vibrate and rotate. And that gives you a whole zoo of energy levels, which could be plumbed as a new quantum resource. And crucially, molecules have a permanent body frame electric dipole moment. And more on this later, but this gives us greater tunability and much longer range interparticle interactions that we can use for quantum simulation. So here's a non-comprehensive timeline of how humans have been able to control polar molecules over the years. It's very non-comprehensive and non-linear. I always have to put the first atomic clock, the thing that AMO physics is very well known for in quantum metrology, was not actually made out of atoms, but it was actually an ammonia molecule fountain clock. Okay, but in the modern era, where does control over ultra-cold polar molecules start? In many ways, the field got a huge kickstart after the group of Debbie Jin and Junyi at JILA in 2008 created the first ultra-cold ground state molecules of potassium rubidium, all prepared in one quantum state. And since then, there has just been very steady progress. First, laser cooling, trapping in optical lattices, long coherence times. The details are too numerous to cover. I just want to give you an overview of, if you're familiar with the progress of technology in cold atoms, a lot of what's happened in cold atoms is now finally happening in cold molecules, albeit with maybe a 20 or 30-year delay. But we are getting there. And I'd like to highlight, in recent years, people have been making degenerate quantum gases of fermions and bosons of polar molecules, which is incredibly exciting. And we think that much more is yet to come. So for those of you who don't work with molecules, maybe an overview of relevant energy scales or temperature scales could be beneficial. Like the hydrogen atom, or pick your favorite atom, of course we have electronic degrees of freedom, electron volt or 10,000 Kelvin. And of course we do have a nuclear spin, so hyperfine interactions. But in between these 2 limits, molecules have 2 degrees of freedom that atoms simply don't possess: the quantized vibration and rotation of the 2 nuclei. And so you see that this spans all colors of light, and all basically wavelengths have been found in a single diatomic molecule. For a molecule to qualify as ultra cold, in my book, the external or kinetic temperature must be lower than all of these other internal degrees of freedom. And then and only then can you prepare a molecule in a single quantum state without some nasty Boltzmann distribution. So how are these molecules prepared? So there have been two very complementary approaches in the past 2 decades. The one that was first accomplished and by far creating the largest number of coldest molecules to date is direct assembly of cold molecules from already ultra-cold atoms. So molecules are very difficult to laser cool in the way that atoms can be laser cool. So our community, we like to cheat. You already take two typically cold alkali gases, and perform a coherent chemical reaction to bind them into a molecule. And this has been astoundingly successful, and to date has 5 independent groups have managed to create quantum gases. So gases so cold that their quantum statistics actually start to matter. Really exciting. Alternatively, there's a specific subclass of molecules that can be directly laser cooled, just like the alkali elements can be. So these are not generic molecules. However, this has been enormously successful starting in 2014 with the first magneto-optical trap. And this method has the advantage that it's fast. Laser cooling is very fast cycle time compared to the first method, which is assembly. And people have loaded beautiful one-dimensional arrays of single molecules and shown single molecule detection and control. However, the temperatures in the second method are still quite a bit deal hotter than what the first method can show. So my talk will be primarily focused on assembled ultracold molecules. So let me give you a step-by-step breakdown on how this can happen, again, following the pioneering work by the Gilla group from 2008. So it is by now standard among many AMO labs to prepare near degenerate or degenerate atomic gas mixtures in some sort of optical trap. That's the first step. Then we use what's known as a magnetic Feshbach resonance to coherently and adiabatically change the state of two free atoms into a weakly bound excited state molecule. So this method is completely reversible. It doesn't inject any temperature into the system. So the temperature that you have of your atoms are going to be the temperature of your molecules. And this creates us an excited state molecule. So on the potential curve, maybe something in the red, which is not really stable and not really dipolar. What we want to work with is typically a low-lying or even absolute ground state of the molecule that has a very, very long lifetime in our vacuum chamber. And so how we do that is a coherent 2-photon transfer. Again, this using 2 lasers, we can make the ground state without injecting any heat into the system. So that concludes my rather lengthy introduction. The rest of my talk will be split into 2 parts. First, let me talk about results I worked on while at Princeton, quantum gas microscopy of polar molecules. So in the group of Wasim Bakker, who I believe has quite recently visited Urbana-Champaign, we decided to kind of marry the technology of cold polar molecules with the technology of quantum gas microscopy. So microscopy is almost exactly as it sounds. It was first developed on cold atoms by the groups at Harvard and MPQ over a decade ago. So what we want to know is if we trap particles in an optical lattice, as denoted by this egg carton potential, can we create high fidelity in situ images of that lattice occupancy? This is a harder problem than it sounds because the lattice spacing is usually sub-micron and it's comparable on the wavelength of the light that the atoms fluoresce. And so we have to be collecting photons with high efficiency with our microscope objective and be diffraction limited, essentially to recreate the occupancy. And this is what we set out to do and basically applying new technology to the platform of cold molecules. One technical slide, how do we form the molecules using 2 ultra-cold atomic species? We create dual Bose-Einstein condensates in a series of different optical trap beams. We compress them into 2 dimensions because for microscopy to work, we really have to be imaging a 2D plane. And then we load these free atoms into this kind of egg carton square lattice potential. Now we perform the molecular conversion and sites that were populated with 1 sodium and 1 rubidium get converted with over 90% efficiency to the ground state molecule. So for microscopy to happen, a lot of the steps need to be reversed. We cannot directly fluoresce the molecules. They don't have what's known as an optically cycling transition. So if we tried to scatter photons off our molecule, they would be excited, but then decay into some dark state and we would lose them. And we would not be able to recreate the occupancy. We wouldn't be able to collect enough photons. So what we actually do is break apart the Feshbach molecule, eject 1 species with an optical blast, and then image the remaining atomic species, in this case, rubidium, by simultaneously laser cooling and fluorescing the atom. And we get these single shot images here on the left, and that's the analog image collected on our camera. And this is the digitization. And this is the filling fraction that we were able to achieve of molecules and rubidium atom at the time of this publication. So even though we had a lot of disorder in our lattice, we were not able to create 100% occupancy of all of the lattice site due to some technical imperfections. This was a first probe of a demonstration of quantum gas microscopy that allowed us to probe correlations between individual molecules in a big ensemble for the first time. Okay, so let's make use of this tool and actually use it to study some interesting quantum many-body physics. So if you've taken any kind of undergrad or grad level solid-state physics or condensed matter class, you probably know that the so-called lattice spin models are often very nice toy models to describe how magnetism arises in quantum systems, right? If you have electron with spin up, spin down, how do they order when the electrons are interacting with each other? Well, since 20 years ago, people have been proposing that you can isolate a 2-level system in a polar molecule and have that exactly implement these famous lattice spin models if you're able to load them on an optical lattice. And so first, let me describe our setup, and then let me describe why we get exchange type interaction. So we induce dipole-dipole interactions essentially with a microwave control. So our molecules are always prepared in the ground, absolute ground state, ground electronic, ground vibrational, ground rotational, and I don't picture hyperfine for convenience here. So we always prepare our molecules in what we call spin state up. However, there is a rotational excitation that occurs about several gigahertz above this ground state, which goes into the first excited rotational state. Let's isolate one of those levels and call it spin down. So these levels are nothing more than the spherical harmonics you know and love from studying hydrogen. So this is actually the s orbital, and these are the 3 p orbitals. It's exactly the same physics. And when you couple into a superposition of these, you get this oscillating dipole in a single molecule picture that oscillates at 4 gigahertz. Okay, why does this give you a dipole-dipole interaction? You might even ask, don't you already have a dipolar interaction? Because you claimed that there's a permanent dipole moment in a molecule. It is true, anytime you pair 2 atoms that are different elements, one of them will have higher electron affinity than the other. So the electron cloud will sit further from one atom and closer to another. This is a permanent body frame dipole moment. But in the absence of a symmetry breaking external field in the lab, when you have an ensemble of these are quantum mechanical objects. There's no direction that the body frame dipole moment points, and they're all random. So your lab frame dipole moment is 0, and you have no net attraction or repulsion. It's a non-interacting, boring system if you just prepare a gas of ground state polar molecules. Not very exciting. So how do you induce an electric dipole moment in the lab frame? Well, let's examine the dipole operator. It's just your typical charge times separation. It clearly couples states of opposite parity. You know this in the hydrogen atom. S and P are opposite parity. S and P states are coupled by an electric dipole transition. For molecules, it's states with odd or even J, which is the rotational angular momentum. So one of 2 ways to induce a lab frame dipole moment You either apply a static external electric field. This will polarize all of the orientation, just like a B field polarizes your magnetic fridge magnets. That's not what we do, although this is the simplest conceptually to understand. Of course, one could have some sort of resonant exchange interaction between two opposite parity states, okay? And this is exactly what happens for a single molecule if you, for instance, couple on resonant pi polarized microwave light between these two orbitals, you'll get this oscillating dipole moment. And if you couple in sigma plus drive, you'll get this rotating peach wave function. So now you understand the picture of one dipole. Let's talk about two, because that's where the dipole-dipole interaction is built up. So how do two dipoles interact in the lab frame? Of course, there's some quantization axis, and how they collide with respect to that quantization axis is denoted by theta. And the dipole-dipole interaction is the same thing you learn in freshman E&M. So if they collide along theta equals 0, always their heads are aligned, so it must be a repulsive interaction. But as they collide towards a 90-degree polar angle, sometimes it's head to tail, sometimes it's head to head. On average, the attraction will be, the interaction will be attractive. And so if you write down the expectation of the dipole-dipole interaction as a function of collision angle, you see that indeed you recover this, highly anisotropic, tunable dipole-dipole interaction in the lab frame. And this we all do with microwaves. Okay, so take what we've learned from the last slide and apply it to an ensemble of molecules in 2D. Next, I will claim, without proof, that we can already natively engineer the so-called XY or spin exchange Hamiltonian, where here X and Y are just the normal Pauli operators of a two-level system. You can write it in terms of the raising and lowering operator. And I find this more intuitive because if you have a rotationally ground and rotationally excited molecule and they're on resonance, that rotational excitation can flip-flop or perform a spin exchange with the neighbor. And always the number of rotational excitations is conserved, which is exactly this Hamiltonian. So this is also called a spin exchange or flip-flop Hamiltonian for that reason. And for us, the prefactor, the strength of the exchange, is nothing more than the dipole-dipole interaction, 1 minus cos squared theta divided by distance squared. And to put real numbers on it, it's roughly Planck constant times a kilohertz for our molecules, for our interparticle spacings. Now, the XY model was first studied in the context of polar molecules, again, in a landmark experiment by the Jin and Yi group. And I think Jake Covey here was also part of this study. And they did a Ramsey experiment and found that the dipole-dipole interaction of nearest neighbors causes a slight sinusoidal modulation of the frequency of the Ramsey decay. And let me also point out that this XY model has been studied in the context of molecules and tweezers by the Chuck group at Princeton and also the Doyle and Nee groups at Harvard. And so what do we do with the quantum gas microscope that's kind of qualitatively new? So we can observe thermalization dynamics of an interacting many-body system prepared and undergoing evolution under this XY Hamiltonian. So again, I must qualify, this is a kind of disordered gas. We don't have 100% of the lattice sites occupied. It's stochastic occupation. Initially, all molecules are prepared and spin up. Then we do a Ramsey pulse, pi half, to quench into the plus X state, wait for some precession time, maybe do a Hahn echo, and then we read out with another pi over 2 pulse. Now, the phase of this pi over 2 pulse is chosen such that in the absence of interactions, up would deterministically evolve to down. We cannot image down state in our microscope. We can only image up state. So after 0 precession time and a pi pulse, we would see the microscope go dark because all of them have become the other rotational state. But what happens as a function of time as these molecules are interacting with each other in the dark? So this is what we can see, the global fraction of spin ups as a function of precession time. And as you might expect, at 0 time, it's nothing. by construction. Everything isn't down. But as time progresses, the dipolar interactions start to dephase the Ramsey sequence. So we first start to see small clusters, typically nearest neighbors, start to appear simultaneously. At intermediate times, bigger clusters, until at late times, the entire system has dephased and about half of our molecules are visible again. But we're not just able to capture a global quantity like total magnetization or total fraction and spin up. We're a microscope, so the power of a microscope lies in measuring particle-particle correlation functions. So this correlator is an up-up spin correlator. It's essentially, if you see an up state on lattice site R, how likely is it to see an up state on lattice site R plus A, where A is some distance away? Okay, here we plot that in this subfigure. At 2 milliseconds, we see that this correlator becomes dark or finite for the nearest neighbors. That means that the nearest neighbors are likeliest to appear together after 2 milliseconds of precession time. That's this picture here. And at intermediate times, the diagonal neighbors come in, until at late times, the entire gas is many-body correlated. We think this means entangled, but we're not measuring entanglement directly. So I can do better than that. I can take this particular square and plot the correlation as a function of the precession time. And here we see something truly coherent stand out and scream at you. So again, these are looking at nearest neighbor correlators, so two molecules that are buddies in the x direction. And we see that they're performing kind of coherent flip-flop interaction, but in phase. And what about the next nearest neighbor, the diagonal pair? Well, again, it's a sinusoidal oscillation, and that frequency is exactly slower from the top frequency by 1 over square root 2 cubed, which is not surprising because the dipolar interaction falls off as 1 over distance cubed, and so on and so forth for further and further neighbors. So what we've shown here are we can do entangling, disentangling dynamics. That's what we see. And if you solve this Hamiltonian exactly for only two particles, you'll see that at certain periods of time, they become up, up, or a Bell state, or down, down, or another Bell state, so on and so forth. So it's very cute. Of course, we can exactly diagonalize this problem. I don't have time to get into this, but we can also implement Hamiltonians beyond XY spin exchange by the method of flow K engineering. Basically, there's a large subset of XYZ Hamiltonians that we can explore with polar molecules, where ZZ is what you would call an Ising interaction. Skip this in the interest of time. To summarize this section, we have a proof of principle that with the polar molecule microscope, we can observe dynamics of about 100 molecules. So starting to become many-body, implementing XYZ type lattice spin models that are relevant for quantum magnetism. And we can investigate to pretty late times in units of interaction time how these systems can thermalize. Of course, the future challenge is decreasing disorder, decreasing spam errors, increasing interaction perhaps, to be able to investigate quantum many-body systems that are out of reach of classical simulation on classical computers. So that brings me to my work, the lab that I'm building currently at UChicago. I've been there for 2 years, and what I feel is one possible new frontier in the experimental platform of polar molecules. So polar molecules have come a long way, but there's still a long way to go. If you look at this axis as, for instance, how cold we can get them, or what kind of disorder we can tame, or how low of entropy of system we can prepare, polar molecules have done a phenomenal job in the past 2 decades, single quantum state control, long coherence times, these simple lattice spin models, controllable 2-particle entanglement, including the first I-swap universal 2-qubit gate recently demonstrated, and very promising for the field, the first degenerate quantum gases, degenerate Fermi gases, BECs. I like to think of us right now as the analog in the mid-1990s for cold atoms, where the first BECs of rubidium and sodium were formed. So we're still in the infancy, And of course, the bottleneck is that we have to go deeper quantum degenerate before we can determine and create phases of matter that are actually qualitatively new, qualitatively distinct than anything that nature gives us, or so we think, including symmetry-protected topological phases, dipolar systems that are superfluids and solids simultaneously, exotic quantum spin liquids that we can actually prepare in their ground states, and near and dear to my heart, I'll talk about it a little bit, possible P-wave superfluidity in a controlled tunable system. So, of course, there are many ways to overcome this bottleneck, and many different experimental efforts around the world are trying different ways to tackle this problem. Many of them are likely to be fruitful. The one that I'm investigating is if we can create a qualitatively distinct new class of molecules that have a very high electric dipole moment. And how will this help us overcome this bottleneck? I claim that there are three maybe semi-independent ways that this might help. But before I get into the details, let me first explain what I mean by highly polar and quantify what I mean by highly polar. So thus far, all assembled molecules have been created out of group 1 alkali elements. That's just out of convenience. As far as I can tell, that's just what our community is best at laser cooling, the atoms that look like hydrogen. Of course, we can cool about 30 elements on the periodic table with varying degrees of sweat, blood, and tears. Now, a molecule is polar if it's made out of two different elements, right? H2, nonpolar, N2, nonpolar. But the more one element pulls on the electron cloud, the bigger the difference in electron affinity, the more polar the molecule is. From high school chemistry, you probably learned about what the most polar bond could be as a pure ionic bond. It's something like NaCl. You pair group 1 with group 7 halogen. It's a pure ionic bond. It's basically as polar as a two-body molecule can get. Unfortunately, we cannot laser cool group 7. They're too complicated. But in 2021, there was a very influential paper, influential for me as I was reading it as a postdoc, that proposed that you could do essentially the same by cooling the coinage metals, copper, silver, and gold, which somehow have very high electron affinity. Don't ask me the reason why, I don't know, when you pair them with group 1. And so dipole moments of up to 10 dBi, comparable to gas phase table salt, are possible. And this is comparable to about 5 dBi for bosonic bialkalis and 3 dBi for fermionic bialkalis. And of course, you win as dipole moment squared. So the upshot is that for achievable interparticle spacings, instead of maybe kilohertz, 10 kilohertz interactions, we could be upscaling to 100 or even 1 megahertz scale interactions. I should also acknowledge there are many other efforts underway to cool alkali coinage metal, including at Johns Hopkins and Durham and Warsaw, and many more being planned with recent early career grants. So 3 advantages of ultrapolar molecules. In the interest of time, and because they're quite technical, I will skip the first 2. You can ask me later. They're more like atomic and molecular physics-y, so maybe not for the general audience. But let me mention one motivating factor, which is if you can increase the interaction strength in a tunable quantum system, maybe you can access qualitatively new physics while remaining at the same temperature. I give you an example. Moire materials like twisted transition metal dichalcogenides, graphene, explosive growth in the last 10 years. And it's not because they've been able to cool their samples to a lower dilution refrigerator temperature. It's because when they twist 2D electron gases together, they can create very flat bands where the interaction energy starts to completely dominate over the kinetic energy. And it is that ratio of interaction to kinetic energy that allows them to see so many exotic phases like superconductivity at magic angles or fractional anomalous quantum Hall effect. I take inspiration from my condensed matter colleagues and start to think if we can increase interaction energy scales, what interesting critical temperatures can we raise? I think one longstanding goal in our community and in condensed matter is to find a superfluid or superconducting P-wave phase that is topological. Famously, the topological P-wave paired superfluid host these Majorana fermions as excitations. And aside from superfluid helium-3, I would claim that the unambiguous characterization of topological P-wave superconductors in the solid state is probably still lacking. And so there have been proposals dating back 15, almost 20 years ago, saying that polar molecules that are fermionic, so composite fermions, they will attract with an intrinsic dipole-dipole attraction. They are already identical fermions. They're not like electrons that have spin up and spin down. If you prepare them all to be identical, then they can only pair in P-wave. They're forbidden to pair it with S-wave symmetry, just by quantum statistics. And so at some critical temperature below, there's an instability to pairing that will just naturally occur. I mean, you know, Cooper taught us all about this. And the only difference from conventional superconductors is that they pair with one unit of orbital angular momentum rather than 0. And so to make a long story short, how can we find identical fermions where this critical temperature as a function of the Fermi temperature is not exponentially suppressed and far beyond what lab temperatures can be achieved? And we think that critical temperatures for potassium silver, which is the molecule that I'm trying to harness in my lab, are going to be so hot in units of Fermi temperature that they are going to be, I wouldn't claim easy to prepare, but at least other molecular species have already done it. So a little bit of molecular physics for the experts on potassium silver. We are very grateful for our collaboration with the group of Michal Tomza, who's able to do these ab initio potential energy curves for the potassium silver molecule. And a few details, the system has an 8.5 dipole moment. We think it can be optically trapped. We think that we can make molecules with Feshbach resonances. Because of the different isotopes of potassium and silver, we can make both fermionic and bosonic isotopes. And a lot of the manipulation, the microwave driving is at a convenient frequency. So here's a timeline and current status of a lab. This is a picture of our laser system and main chamber with a glow from a high-powered UV laser. And grad students Michael from UIUC and Angela have been instrumental over the past 2 years. We started in a temporary lab space, started tackling the easier element, potassium, moved to a new lab space, and pretty quickly got the harder element, silver, under control in a magneto-optical trap. And now we're performing extended cooling, you can say sub-Doppler cooling of silver in preparation to optically trap it and be a true dual species experiment. This is a picture of the apparatus. Many of you have worked with very similar things in your lab. In many ways is a standard quantum gas experiment with a silver oven and a potassium 2D Mott source combining together at the main chamber. And here's a picture in real life. So slowing, cooling, and trapping of silver was something that we had to really work hard to tackle because it is very unconventional in the world of ultracold atoms. Silver, you might know from undergrad quantum mechanics, about 100 years ago, it was the first thing that humans manipulated in the lab that showed us that there was spin, right? That there was quantization of a magnetic moment in the famous Stern-Gerlach experiment. But since then, silver has not had such an illustrious history in atomic physics, so we try to make silver great again. And here is the laser cooling transition of silver. It's in the UV, 2 lasers is all it takes. And here's a fluorescence image of various magneto-optical traps we're able to prepare with silver. I acknowledge that all the way in 2000, there was a group, Herbert Walter, I believe, and Max Planck, that actually made a tiny Mott of silver. Very impressive, because UV technology was way worse back in the day. And also I acknowledge my friend and collaborator, Dave DeMille, at Chicago, moving to Hopkins. Their group also has a silver Mott on the way to making francium silver molecules as a next generation electric dipole moment precision measurement experiment, more for fundamental physics. So last or second to last slide, the next steps are demonstrating that deep subdoppler cooling will work. Basically, if we have it at about 1 millikelvin, it's not cold enough for us. We want 10 microkelvin. And last week we saw our first hints that we could really cool and compress the gas in multiple directions with this subdoppler cooling mechanism. And for the rest, typical atomic physics techniques, but applied to two very different species will be difficult, I think, but eminently doable. And the end goal is, of course, to make molecules. So with that, this is my final slide. I leave you with an outlook of perhaps using polar molecules or ultrapolar molecules might be a good test bed for quantum simulation of exotic types of magnetism, superfluidity, and also exotic quantum thermalization, something known as quantum many-body scars that do not thermalize in ways that we expect. I would also mention that I have a second experimental effort recently started, which is to combine the platform of single ultracold molecules with a high finesse optical cavity. And the reason to do so is motivated by quantum chemistry, especially photochemistry. If the cavity environment can really change the density of states of the electromagnetic mode, perhaps we can change the chemical reactions that depend on coupling to the background EM modes in a tunable way. And this, I'm very happy to collaborate with Jake. So finally, I'd like to acknowledge the people who did the work. Grad student Michael and Angela and undergrads Xiaoyu and Jolie are working on potassium silver. Nachiket is a grad student building the cavity experiment. Also like to thank my collaborators, Dave, Ruben, Mahal, Tice, as well as Jake, who's, I'm also involved in his helium in tweezers. I'd like to thank the funding agencies and thank you for your time.
Right. Well, are you building a microscope in your?
We did buy a microscope.
Okay.
We installed it and then ripped it out when we needed more optical access temporarily. The plan is to do bulk physics first, like the superfluid actually does not require any form of optical lattice. And the kind of more low-tech absorption imaging, right? Pass light through a cloud and see the light attenuate, that would work just fine for what we're trying to do first. But eventually, we would like to load single molecules in a lattice in there. We need a microscope.
In your picture where you had the funnels showing the bottom, can you just go back to that? Right, so there's kind of a bunch of exotic things, none of which I know. Which of those animals in the further regime is most interesting to you, or would you most like to be spend time with?
I would love to do quantum simulation of things that are not predicted by my laptop computer. And of course, this is a big challenge for any quantum simulator, right? Going to true quantum advantage. And for me, that means studying, finding maybe a phase of matter that is qualitatively different than what has been found in nature. So I'm really interested in P-wave superfluidity or supersolids, which are, they're coherent like a BEC, but they break translation invariance just like a solid. So.
And how does the scaling of the simulatability of that with your laptop go with the number of lattice sites that you actually have?
A lot of these.
Presumably, if you have just 3, you can simulate that better.
Absolutely. A lot of these are actually in free space. So I know my first talk motivated, oh, lattices are so cool. And then the second half, a lot of what I wrote on the bottom happened even in the bulk in free space. And this is very complex because you have itinerancy, you have motion, you have momentum in maybe 3 or 2 dimensions, and they're all interacting. So it doesn't take more than, like even a few body problem in the true free space is very difficult for a laptop to simulate. Yeah.
could you please describe how does Yan mode density affect chemistry?
Yeah, absolutely. So this is not my idea. First of all, let me be clear. For the past 10, 15 years or so, there's been a burgeoning field of cavity chemistry or polariton chemistry from the typically physical chemist community. And a holy grail for them has always been coherent control of a chemical reaction with light. And in the early 2010s, there were a few reports that I put some solution phase molecules in an optical cavity, just a Fabry-Perot cavity, and I changed the cavity length. So I changed the resonant frequency of the mode. If that mode couples to a vibrational or electronic transition in the molecule, I can change the outcome of the molecule-molecule reaction. So instead of A plus B equals C plus D, maybe it's A plus B only equals C and no D, right? This would be the holy grail if you could do this at some industrial scale, maybe catalyze some important reaction. And the challenge in the cavity chemistry community is that they're working with room temperature, hot molecules, all populating many, many different modes. Many modes of the cavity are talking to those molecules. It cannot be written down with a Hamiltonian and have that Hamiltonian guide your intuition of what happens with a chemical reaction. And maybe more disturbingly, a lot of the earlier experiments were not replicated by independent groups. So I would like to build a much simpler but more controlled version of these experiments, looking at even simple photoassociation reactions. Atom plus light equals molecule, but that final molecular state maybe can be tuned by tuning my cavity parameters. So I'm going to use a fiber cavity platform in the cavity QED regime to try to achieve high cooperativity and see if this is possible. But microscopically modeled with a Hamiltonian. Yeah. Yeah.
You talked about correlations from the microwave photon drive as opposed to switching on the dipole interactions by putting an electric field on early on in your talk. So you said there are two ways to get the dipole-dipole interaction. One, polarizability, and the other is right. So could you do both? And would you get
Absolutely. In fact, there's a theory paper by, Alexei Gorshkov, Michael Lukin, Anna Maria Ray, I think dating 10 years ago, saying that you can have a fully tunable kind of extended TJ model if you allow your molecules to be manipulated simultaneously from microwave and DC electric field. In practice, this is kind of very experimentally challenging. Microwaves are cleaner in many ways than putting in DC electrodes in your chamber and, eliminating all of your unwanted curvature and everything. But I would say that Junyi's latest experiments have started to probe in that direction of maybe simultaneously using microwaves and electric fields with KRB molecules.
Any more questions? Let's thank Zoe again.